Hello everyone. In the previous lecture we discussed transient flows through horizontal and vertical columns, or the transient flows without influence of elevation head and with the influence of elevation head we have considered, and we got analytical solutions. These equations are called Green and Amt equations. This is given by the two gentlemen, Green and Amt, in 1911. Very old literature. These particular equations, this is for the horizontal flow. The x by square root of time is equals to square root of 2 ks times h naught minus hi by theta naught minus theta s. Here theta naught or theta s. So here x is the spatial distance and t is the time, and ks is the saturated hydraulic conductivity of the soil. H naught is a positive head you maintain. It could be 0 or more than 0, and HI is the initial head, and theta S is saturated volumetric water content, and theta I is initial volumetric water content. Similarly, for the vertical flows, you have this expression. Instead of x, you will have the independent variable z. Here this expression is implicit, and you can obtain for a given time what is the wetting front location in the vertical direction can be obtained using this particular equation. Here the z is assumed to be positive upward. So when there is a infiltration against the gravity that is taking place, then we have used positive value for z, and this is the expression for this. Again, once again I remind you that these expressions are derived in 1911. So when the computation was nearly very costly, and during that time these analytical expressions for the transient flows were derived. These expressions can be used for the coarse grained soils, but not applicable for fine grained soils, because sharp wetting front generally you do not find for most of the soils, but that approximation can be borne for coarse grained soils, for some coarse grained soils. Interestingly, capillary rays in soils has been studied slightly little earlier by Buckingham in his classical work on studies on the movement of soil moisture, which is published in 1907, a very old work, which is a classical work in soil science literature. In this particular work, he had established the rate of capillary rays. He found the capillary rays data with time for several soils. The experiment involves somewhat like this. This figure is not from this work. This is a setup from our lab at IITG, and you will have a soil column. It could be sand column in this case, and you have a reservoir, water reservoir. These two are connected through these pipes. So you have a water table maintained at particular level. So this is the water table that is maintained, which can be read on this scale. So when the water table level in the reservoir is this, at equilibrium the water table level in the soil also is expected to be here, somewhere here. So this is the water table, and z is measured upward positive from here onwards, and here you can see the capillary rays that is taking place, and capillary fringe can be seen, the fringe, the way the water moves in sand, which is called capillary fringe, it can be seen here. So the rate at which the movement of water takes place within the soil mass was obtained for different soils where the porosity values were different and our compaction densities could be different, therefore the porosity varies or the saturated hydraulic conductivity varies. Then at equilibrium, what is the maximum capillary height that was achieved, that was found, which is indicated with Hc, capillary height. So for these three different values, for example, the capillary height values for different soils were tried to correlate it. This capillary height is correlated with different soil pore size distribution parameters by several researchers afterwards also. For example, several works in later on were conducted by Lane and Washburn. This is in 1946. He established a relationship between Hc and D10 of soil. Hc measured in millimeter, and here minus 990 log D10 minus 1540. This is one empirical equation he derived by conducting experiments on several soils, and here D10 is also substituted in mm. So, Hc was predicted using such empirical equations. So, this is one such empirical equation. Another empirical equation given by Peck et al. This is in 1974. So, here the Hc is equals to C by E D10. Here D10 is substituted in mm, and C has units of mm square, and Hc has units of mm. E is the wide ratio, and C generally it varies between 10 to 50 mm square. So, such empirical correlations are available for predicting the capillary raise or capillary height for different coarse grained soils generally, because for fine grained soils it takes enormous time to reach equilibrium, and moreover the height will be very significantly high. Little afterwards, in 1943, Terzaghis infamous book Theoretical Soil Mechanics provides one solution for rate of capillary raise. The rate at which the capillary raise occurs in soils, a simple analytical solution is derived, which has some interesting aspect which I will discuss after the derivation. So, which is again he assumes that the Darcy's law is valid. So, he uses q equals to minus ks I, q equals to minus ks I, and q we substitute the flux or the Darcy velocity as earlier we substitute as n times dz by dt. So, this is velocity and this is porosity of the soil. So, this is equals to minus Ks. He assumes that the saturated hydraulic conductivity is still valid for this particular soil, because he also assumes that there is a sharp wetting front exists within the soil when the capillary raise takes place, which assumption is similar to Green and Amt equations. So, here he assumes the gradient that governs for the flow is Hc, the capillary height, minus Z, which is the distance. For example, this is the water table within the soil mass, and Z varies upward, and which is now if this is the capillary height. So, this is the capillary height Hc minus Z, which is the head that controls, and distance Z. So, this is assumed to be the gradient for the flow. So, when Z is equals to 0, there is a this gradient becomes infinity, that means it wants to achieve this value, and when Z is equals to Hc, that means it reaches the capillary height, then gradient becomes 0. So, this is a hydraulic gradient he used. This expression is very much similar to the Green and Amt equations which were given in 1911 and this is in 1943. So, we can understand that rate of capillary raise equations are derived based on existing Green and Amt model for the transient flows through soils during that time. So he further he simplifies this expression. So if we simplify this, so you get this expression z dz by hc minus z is equal to minus ks by n integral dt. So after rearranging the terms, all z terms are taken into one side and time terms are taken on the other side, and we integrate on both sides. Then so this can be simplified further into if you put minus here and add hc to it, I will put dz somewhere here and minus hc, then this expression becomes minus first two terms if you use, this is minus dz plus hc times dz by hc minus z is equal to minus ks by n, this is time t plus constant of integration. So this is what results, and this is minus z plus the integration of dx by a minus x is minus log a minus x. So therefore so this becomes minus hc log hc minus z, that is equals to ks t by n plus c. If we invoke the initial condition, that is at time t equal to 0, z is equal to 0, there is no flow, there is no raise. So then if we invoke that, the c is equals to minus hc log hc minus z, sorry hc. So this is the value for c. If we substitute, we get minus z, then if you bring this value this side, plus hc minus plus hc log hc minus hc log hc minus z minus ks t by n. So this can be written as minus z minus of hc if you take common, or plus hc if you take common. So this simply becomes log hc by hc minus z is equal to minus ks t by n. So therefore the t is equals to n by ks. If I take common hc also, then log, see if I put ks here plus ks here, then everything should be fine, I think. Then this is simply, so this is plus ks, then everything is fine then. So t is equals to minus n t by ks times hc log hc by hc minus z by hc. So it assumes the validity of Darcy's law, general Darcy's law, that is we consider total head here. So if we consider that, this can be written as minus ks, the hydraulic gradient he considers is hc, that is a capillary height, minus z divided by z. This form is very much similar to the Green and Amt equations which are derived or given in 1911. If you notice the time interval, the Terzaghis expression is given in 1943 for the capillary raise rate, and by then already the Green and Ampt equations are available for transient flows through unsaturated soil. So therefore, it is very much clear that Terzaghi has considered the Green and Ampt equations for the derivation of capillary raise rate in unsaturated soils. So here this expression Q equals to minus Ks times this one if it is written, and here the Q is similar to the Green and Ampt. There theta s minus theta I it is written. So here initially the soil is assumed to be completely dry, then theta I is equals to 0, then that is theta s, which is nothing but n, times dz by dt, that is a velocity term. So then this is the flux is equals to minus Ks. Again he assumes that the saturated hydraulic conductivity prevails, because he assumes that there is a wetting front, sharp wetting front exists during the capillary raise, which is similar to what shown here. If this is the water table location, and above this the z, the elevation is shown with z, and if this is the capillary height hc, then the gradient is considered to be hc minus z, that is a head that governs the flow, divided by the z at any given location. For example, at z equal to 0, so it becomes infinity, that means so the gradient is with full capacity, it has infinite gradient or large gradients. So when z is equals to hc, that means when the flow reaches the estimated capillary height, so because the capillary height should be known in this particular equation, if it reaches the capillary height, then the gradient is 0 and the flow stops. So that is the expression for. When we simplify this, here we need to observe one thing. Here as we are writing, the flow is taking place from higher head to the lower head, because this is the higher head and it is taking towards the lower head. This should be positive value, and then you will get positive quantities and it is solvable. Now when you simplify this particular expression by rearranging the terms on both sides, you get z dz by hc minus z, and integrate on both sides. So you get n, if I take it on the other side, ks by n, and integrate the dt term. So then if we integrate this, we can simplify this a priori. So you can take negative here and put negative here, and then you can dz I will write here, then I can add hc and deduct hc. So then I can simplify this as dz minus dz. If I write the first two terms, then this is 1, so therefore minus dz, and plus hc integral dz by hc minus z, which is equals to ks by n t plus an integration constant. So this expression when you solve, here this is a minus z plus hc. So the integration for this is 1 by a minus x is minus log a minus x. So therefore the integration for this is, you get negative here, minus hc log hc minus z is equal to ks t by n plus c. If we invoke the initial conditions, the initial condition is at time t equal to 0, z is equals to 0, there is no flow, the capillary raise is 0. So therefore c becomes minus hc log hc. So, if I substitute this constant here, you get minus z and take the c on the other side plus Hc log Hc minus Hc log Hc minus z is equal to Ks T by n. Then if I simplify this, minus z plus Hc log Hc by Hc minus z is equal to Ks T by n. So, this can be further written as T is equals to n by Ks. If I take the Hc common, this is log Hc by Hc minus z minus z by Hc. So, this is the expression given by Terzaghi in 1943 in Theoretical Solid Mechanics book, and this expression is an implicit expression describing the rate of rise. So, there is some problem with this figure here. So, ignore this soil 2 figure, it should be somewhat like this. So, there is some issue and then you can ignore this soil 2 data, you can only assume the soil 1 data. Now, let us see. So, the expression for time t is equals to n Hc by Ks times log Hc by Hc minus z minus z by Hc. Here for a given soil, so you take soil 1, the porosity of the soil is known, Ks of the soil is known, Hc should be determined or Hc should be known. The capillary rays at equilibrium should be known for a given soil. Then if such information is known, one can predict the rate at which the capillary rays takes place through partly saturated soils can be determined. So, for example, if this data is given, this particular data is given, we substitute for time equals to at any given say space. Here it is an implicit form, therefore, what is the time taken for reaching the capillary rays to given elevation can be found. So, for example, the time required to reach a 0.1 meter, 0.01 meter can be obtained. So, which is n equals to 0.31 times Hc is 0.284, which is substituted in meters. Ks again substituted in meter per second, this is 1.6 into 10 power minus 4, the data is taken from here, times log Hc is 0.284, this should have been smaller letter, small Hc, 0.284 divided by 0.284 minus z, I said 0.01 meter, minus 0.01 meter divided by Hc 0.284. So, this comes out to be a very small value, 0.39 seconds. So, to reach 0.01 meters, it hardly takes 0.39 seconds for this particular soil having these properties. Similarly, when z is equals to, here z is equals to 0.01 meter, if z is equals to 0.1 meter, the time required is 45 seconds. So, in this manner, using different data points at different heights or elevation, the time are found and drawn in this manner. So, this is the data, somehow there is a error in plotting, so dimensions, so this is somehow distorted, but the data should have been like this. So, as the hydraulic conductivity decreased nearly twofold, so this is for soil 1, right. So, this is for soil 2, this is for soil 1. So, the color also there is some error in this, while copying from a spreadsheet there is a error in or the entire figure got distorted. As the capillary height is 0.82 for soil 2. So, this is the data for this, and 0.284. So, the data somewhat like this, it should come here 0.284. So, this is soil 1 and this is soil 2. For the soil 2 data, the capillary height is 0.82 and the rate is very small because it is taking nearly 8 days to reach the equilibrium, because the hydraulic conductivity is 10 power minus 6 meter per second. Here the equilibrium time is very less, hardly 0.03 days or nothing but few seconds, because the hydraulic conductivity is 10 power minus 4 meter per second. So, with this one can use Terzaghi's expression, which is a very simple expression to find out the capillary raise rate. However, researchers have found that the Terzaghi's expression overestimates the capillary raise rate. This is because especially the limitations in the expression. One of the major limitation is that he assumes that the saturated hydraulic conductivity for the soils, he uses saturated hydraulic conductivity for K. So, which is a major limitation, and in 2004, after 1943 and Liu and Lycos in 2004, they have given an expression by modifying the hydraulic conductivity function. So, they use the same expression here, K times Hc minus Z by Z. So, everything else is same. Instead of K is equal to Ks, they use Gardner's expression. They use expression for K as Ks times exponential of alpha Hm. So, this is what the expression they use, and they got a closed form analytical solution, which is Ks times T by N, which is similar to what we got, is equals to sigma j equals to 1 to m alpha power j divided by j factorial times minus sigma s equal to 0 to j Hc power s into z power j plus 1 minus s divided by j plus 1 minus s plus Hc power j plus 1 log Hc by Hc minus z. This expression will be same as Terzaghi's expression if the series form is not considered, if j is equal to 0 to m equal to 0. If you substitute m equal to 0, this expression will converge to Terzaghi's form. So, the Liu and Lycos in his in their paper rate of capillary raise in soils, published in AEC journal, they showed that this particular expression is a very good match for coarse grained soils for predicting rate of capillary raise when compared to Terzaghi's expression. Terzaghi's expression overestimates significantly. So far we have seen several preliminary expressions for transient flows through unsaturated soils, but in 1931 one researcher called Richards had given an expression for transient flow through unsaturated soils. This expression is even now it is used. This is based on Darcy's generalized Darcy's law and combining with mass conservation expression, which I discussed earlier also, which involves considering a unit volume, considering a representative volume. When the flow takes place through this representative volume, say Qz in the upward direction and Qz plus delta z, because this quantity is delta z and this is delta x, and other direction is delta y. So, the flux which is this is a volumetric flux. So, the volumetric flux which is going into the element is volumetric flow rate Qz of the water which is entering into the element elemental volume is, that is Darcy's velocity Qz times cross sectional area delta x delta y. Similarly, the amount which is coming out is Q z plus there is some change in the flux dou q by dou z times delta z times delta x and delta y. So, this change exists. There is a, what is the difference between these two? The difference is dou q minus dou q by dou z times delta x delta y delta z. So, this difference exists if this is a transient flow. So, in the transient flows, this is equal to what? So, this is q has units of meter per second. So, this is equal to, this quantity is equal to the change in volume of water with time, because there is a change in the volume of water. And when water is water content increases in this particular element, then the volumetric flow rate also changes. So, therefore, in transient flows this is equal to this. If you look at the dimensions, this has units of meter per second and this has meter and this is meter cube. So, this has units of meter cube per second, and here volume of water is meter cube and t equal to time. So, dimensionally this form is correct, this equation is correct. Now, this can be written as dou theta by dou t times volume element, because theta is defined as volume of water by total volume. So, this can be written as this. So, therefore, the expression which you get using mass conservation is dou q by dou z is equal to dou theta by dou t using mass conservation. If you use generalized Darcy's law to express q, then this becomes dou by dou z of minus ks gradient. So, that is a d or dou h by dou z. This is a head, the hydraulic potential varies in the vertical direction, that is why the flow is taking place only in vertical direction. So, that is why the gradient is dou h by dou z is equal to dou theta by dou t. So, this expression dou by dou z of, sorry, this should not be ks, this is k. So, this is unsaturated hydraulic conductivity times k times dou h by dou z is equal to dou theta by dou t. This expression is Richards expression, Richards equation. This is a very famous equation which is even now used for solving transient flow problems. So, this original expression is in mixed form. It is called mixed form because the dependent variables on one side, the right hand side is theta, volumetric water content, and the dependent variable on the left hand side is h, suction head, are present as dependent variables. This form is called mixed form. This can be written in the other form as dou by dou z of k dou h by dou z. By using chain rule, you can write this as dou h by dou t times d theta by dh. So, this quantity is a slope of your soil water characteristic curve, C theta it is called. This quantity is called specific moisture capacity. So, this is head form, because when you have a smooth soil water characteristic curve function, smooth function of soil water characteristic curve, the slope can be determined, and then if you solve, you will get h of z comma t using this expression. So, this is called head form. Similarly, You can write this expression as a dou by dou z of k. This can be modified again using chain rule. This can be written as dh by d theta times dou theta by dou z is equal to dou theta by dou t. So, this particular quantity is called diffusivity, hydraulic diffusivity d theta, which may be different from diffusion coefficient, which is used in ion diffusion. This has units of meter square per second because it has units of meter per second, and h has units of meter. This has units of meter square per second. This is called hydraulic diffusivity. So, this expression finally is dou by dou z of d theta times, or I will write it here. This expression is dou by dou z of d of theta dou theta by dou z is equal to dou theta by dou t. This form is this form. If you solve, you get theta of zt. So, this is called theta form. Many researchers have studied all these by using several numerical techniques to solve these expressions and get the solutions. They found that the mixed form gives good solution because it does not approximate any mass conservation principles, but head form was found to be not conserving the mass, and which gives erroneous results. And this particular form we have utilized earlier for when we discussed multi-step outflow technique. This is again simplified further into this particular form, dou by dou z of d of theta dou theta by dou z is equal to dou theta by dou t. This particular form, when we simplified, we assumed that the variation of d with respect to z is ignorable, then we assumed that the variation of theta with respect to h is linear, then we got an expression for dou square h by dou z square equal to dou h by dou t. And then Richards provided analytical solution for this particular expression, and we estimated d theta, and from knowing d theta and solved characteristic curve, we estimated k theta earlier. So, this Richards expression is a very popular expression, a popular equation which is used for solving many problems. In this expression, dou by dou z of k dou h by dou z is equal to dou theta by dou t. This is the mixed form we wrote. If the flow is taking place in vertical direction, this will be transformed into k. Here h consists of both matrix suction head and plus elevation head. If we consider upward positive, then if there is a infiltration taking place in upward direction or evaporation taking place from initially saturated soil, then this expression becomes dh by dz plus k is equal to dou theta by dou t. If you consider this is negative, then you get minus k, because when we substitute h is equal to hm plus z, you get this expression. So, this is expression for vertical flows. Vertical flows are the influence of gravity is considered. This expression is valid for horizontal flows, or the influence of gravity is ignored. For the expression which I just discussed, that is theta form, that is dou by dou z of d theta of dou theta by dou z is equal to dou theta by dou t. For this particular theta form, researchers derived analytical solution earlier, so which is called Boltzmann transformation. So this particular derivation can be found in Lou Lycos textbook or many other resources like Rumnin, which is published in 2012 on subsurface solute transport models and case histories with applications to radionuclide migration, and many other researchers in many other literature also this particular formulation is provided, and all most of the soil science literature will have the derivation for this particular form of expression, form of equation using Boltzmann transformation. So because this is a partial differential equation, the analytical solution for this particular nonlinear form of equation is not possible, difficult. So therefore, if this two dependent variables can be transformed into z and t, for example, if this is a horizontal flow, then it will be better if you write x, that means this is a horizontal flow. So the influence of elevation or gravity is not there. So for this particular form, you have two independent variables like x and t. If these independent variables can be transformed into one independent variable, then this can be this will become a simply ordinary differential equation, then solutions may be possible. So this concept is utilized based on Boltzmann transformation. So here the simple boundary conditions are considered. The boundary conditions are theta x equal to 0 and time any given time, this is equal to theta s, and theta at x equal to infinity at any given time, this is equal to 0. So this means that you have a infinite column, that means very long column, long soil column, which is connected to, you may have some porous stone or something here, porous plate, and which is connected to a reservoir. So when the flow takes place through the soil mass, you discard the experiment or you stop the experiment before the flow reaches the other boundary. This is x equal to infinity boundary, and this is x equal to 0. At time t equal to any given time, so theta is equal to theta s all the time. So at this point, this is a saturated water content, this is saturated water content at any given time, and the flow does not reach the other boundary. So now the independent variables theta of x t, these are independent variables, the independent variables x t, if they can be transformed, theta of x t can be transformed to one independent variable, that is lambda, so and where lambda is equal to x by square root of t. This is called Boltzmann transformation. This is called Boltzmann transformation. Now how to convert this? So the dou theta by dou x terms, so this can be written as dou theta by dou lambda times d lambda by dx using chain rule, but as the theta is now dependent on only one single independent variable, this will be d instead of dou. So this is d theta by d lambda, and this is this is dou lambda by dou x. So if lambda is equal to x plus square root of t, this is d theta by d lambda times d lambda by dx is simply 1 over 1 by square root of t, Similarly, dou theta by dou lambda is equal to d dou t, sorry, dou theta by dou t, dou theta by dou t is equal to d theta by d lambda times dou lambda by dou t. So, this is equal to d theta by d lambda times this one is nothing but minus x by t root t, because the derivation of d by dx of 1 by square root of x is minus 1 by 2 x root x, right, because this is x power minus half, and the derivative is simply minus half and x power minus 3 by 2. This can be written as 1 by 2x minus 1 by 2x square root of x. So, similarly here x is t. So, therefore, d theta by d lambda into minus x, x remains there, and you are derivating partial derivative, only derivative for t is considered. So, therefore, minus x by t square root of t. So, if you substitute these into the main expression, then dou by dou x gives d by d lambda of 1 by square root of time t, d by d lambda d theta, and dou theta by dou x is again d theta by d lambda, and 1 by square root of time can be taken out, and this expression which is equals to, so dou theta by dou t is minus x by square root of t is again lambda from the Boltzmann transformation. So, this is simply minus lambda by t d theta by d lambda. If you get 2 here, so as this t gets cancelled on either side, this expression simply becomes lambda by 2 d theta by d lambda plus d by d lambda of d theta by d lambda is equal to 0. So, this is a ordinary differential equation. This can be solved by integrating. The boundary conditions will be transformed to theta of x equal to 0, means lambda is equal to 0, this is equal to theta s, and similarly when x equal to reaches infinity, lambda also reaches infinity, which approaches to infinity, which is equals to theta initial value could be 0 or anything. So, then if you integrate it, then you get value for if you integrate twice, then you get d theta. So, then d theta can be written as minus half d lambda by d theta at theta initial to theta s lambda of theta times d theta. So, this is the solution for the theta form of Richards equation by considering the Boltzmann transformation. So, essentially when you conduct such an experiment, when you obtain the variation of theta with x and time, if you get, then this can be transformed to, this can be written as theta of lambda if that information is known. So, how lambda varies with theta or theta varies with lambda, that is known. So, because lambda is simply x by square root of time. So, for different values of x and different values of time, if you get the data of theta, then this can be compiled, and the theta of lambda or lambda of theta can be written. Once the data is substituted here, you can get d of theta. There is a diffusivity. How diffusivity changes with volumetric water content can be obtained using this particular expression. So, from the measurements of theta of xt is measured from the data, from this particular data, which is converted to theta of lambda or lambda of theta. So, then from this, using this expression, d of theta can be obtained. The diffusivity changes with volumetric water content. Thank you.